about the Nyquist stability criteria. We will study that how this Nyquist stability criteria is used to find out the stability of a closed loop control system. So let's start with our topic. We know that whenever we want to find out the stability of a control system, then we find out the roots of the characteristic equation. So the stability analysis So the stability analysis of a feedback control system means that it is a closed loop control system. And this stability analysis is based on identifying the location of the roots of the characteristic equation on the S plane. So this is the S plane. This is imaginary axis and this is real axis. So on the S plane, if the roots of the characteristic equation, they are lying on the left hand side, then the system is said to be stable. And if the roots are lying on the right hand side of this S plane, that is right hand side of the imaginary axis, then the system is said to be unstable. That is, whenever we want to find out the stability of a feedback control system, we just find out the location of the roots of the characteristic equation on the S plane. Okay, now this stability, it is of two types, that is the absolute stability and the relative stability. Stability, it is of two types, absolute and relative. Absolute stability means that the stability of the system when certain parameters are variable, like we vary some parameters of the system, and according to that variation how the system is responding, that is how the response of the system is changing. So that is called the absolute stability. That is what is the stability of the system according to the changes in the parameters of the system. Now relative stability, it shows that how the system is stable, how much the system is stable, that is it is giving us the quantity of the stability, whereas the absolute stability, it defines the quality of the stability. Okay, now for to determine the stability, that is the absolute and relative stability, there are various methods. And for absolute stability, the methods are like Routh-Hurwitz. We have already studied in our earlier videos that Routh-Hurwitz we have studied root locus. Okay, so all these methods, they determine the absolute stability of the system. They don't give us any information about the relative stability, but this Nyquist stability criteria, it gives us information about both the absolute and the relative stability. So whenever we want to find out the relative stability of the system, we can use this Nyquist stability criteria. So, what is this Nyquist stability criteria? Let us study it. The Nyquist stability criteria, it is a graphical method of determining the stability of the system. Okay, so this method is based on some graphical method. It is a graphical method of determining the stability, and both the absolute and relative stability can be found out. And as all the stability criteria, they are just based on finding out the location of the roots of the characteristic equation. So this Nyquist stability criteria, it is not based on finding out the location. It just uses the frequency response of the system. So it is based on the frequency response. Okay, and using this method, what we are finding out, we are finding the stability of a closed loop system using its open loop frequency response. So using this method, the stability of a closed loop system can be found from the open loop okay. So using this method, what we are finding out, the stability of a closed loop system, and using the open loop frequency response. No need of calculating the loop roots. Okay, we don't calculate the roots of the characteristic equation just like we do in the root locus and the root Hurwitz criteria. So here only the frequency response will be used. So using this Nyquist criteria, it is used to identify the so using the Nyquist criteria, we just identify the presence of the roots of the characteristic equation in a specified region of S-plane. That is, we are not calculating the roots of the characteristic equation. We are just saying that where the roots will be located without calculating it. Okay. So this Nyquist criteria, it is convenient because here we are not calculating the roots of the characteristic equation. So if we are not given the mathematical model of the system, there are sometimes cases when we are unable to find out the mathematical model of the system. It is not available to us, and only the frequency response is available. So using this frequency response, we can find out the stability by using this Nyquist stability criteria. So it is convenient because Okay. Now this Nyquist stability criteria, it is based on polar plots. Okay, and we can say that the Nyquist plots, they are in continuation of the polar plots. Okay. So Nyquist plots are continuation of the polar plots for finding the stability of the closed loop system by varying the omega from minus infinity to infinity. In polar plots also, we plot the magnitude and the phase angle of the closed loop transfer function, and we vary the value of omega from minus infinity to infinity. So these Nyquist plots, they are just, we can say that they are continuation of the polar plots. In Nyquist also, we are going to first plot the polar plot, and then we are going to add some further steps in this. So these Nyquist plots, they are based on the polar plots, and the value of the omega, it is varying from minus infinity to infinity. So Nyquist plots are used to draw the complete frequency response of the open loop transfer function. Okay, that is complete frequency response can be plotted using the Nyquist plots. The Nyquist plots, they are developed by the scientist H. Nyquist, and on the name of the scientist, the method has been named as Nyquist stability criteria in 1932. Okay, so let's study that what is this Nyquist stability criteria, how we find out the stability using this method. Before starting with the method, there are some definitions which you should keep in mind, that what these definitions are known, because these basic terms, they are going to be used in this method. So let us study the few basic terms. The first basic term which we will use in the Nyquist method is contour. So what is a contour? Contour is a closed path in a complex plane. Complex plane here will be the S plane. S plane is a complex plane, okay, because S is equals to sigma plus j omega, okay, having both real and imaginary parts. So when in this S plane, if we have any closed path in it starting from a point and ending at the same point, then that will be known as contour. Second term is Nyquist contour, or we can say Nyquist path. Okay, so what is a Nyquist contour or Nyquist path? It will also be a closed path or closed contour in the S plane. Okay, so Nyquist contour or Nyquist path, it is a closed contour or closed path in the S plane which completely encloses the entire right hand side of the S plane. So this is the S plane. We know that if the roots of the characteristic equation, they are lying on the right hand side, then the system is unstable. So what we are doing, we are enclosing this entire right hand side by a closed path, and this closed path will be called the Nyquist contour or Nyquist path. So this is the Nyquist contour or the Nyquist path. So it is a closed contour or closed path which is enclosing the entire right hand side of the S plane. So for enclosing this right hand side plane, this is the S plane, it is imaginary axis, real axis, and this is the right hand side. So for this, we will draw a semicircle whose diameter is very large and whose center is at origin, and it is enclosing the entire right hand side of the S plane. So for this Nyquist contour, in order to enclose the complete right hand side of the S plane, a large semicircle so in order to enclose, we are drawing a semicircle whose diameter is very large and the center is at origin. So that complete right hand side is enclosed in that path, and the radius of the semicircle is infinity. So this is the Nyquist path, or we can say the Nyquist contour. Now the next term is Nyquist mapping. So Nyquist mapping is the process by which a point in the S plane is transformed into a point in F, which is given in to us in the S plane. It is transformed into a point in Fs plane. It is called mapping, and this Fs function is called the mapping function. So what we are doing, we are having a point in the S plane. We are transforming that point into the Fs plane, that is the frequency plane, j omega plane, we are transforming. So this type of mapping is called the Nyquist mapping. Now next term is encircled. So a point x so if there is a point x, then that point x is said to be encircled by a closed path if that point is lying or it is found inside the path. Okay, let's take an example. We are having a point which is lying inside the closed path. So this is a closed path. Okay, we are having a point X here and a point Y here. So this point X is said to be encircled by this closed path because it is lying inside this path. Why is this point Y? It is not encircled by this closed path because it is lying outside this closed path. So X is said to be encircled and the point Y is not encircled by the closed path. So this term encircled, whenever we use it in the Nyquist method, that whether this point is encircled or not, then we have to just see that whether it is found inside that path or outside that path. Next is enclosed. So any point or region, it is said to be enclosed by a closed path if that path is traversed in the clockwise direction and point is found to lie in the right of the path. That is, we are traversing the path in the clockwise direction, and while in the clockwise direction, the point is lying on the right hand side of this path. The point is said to be enclosed by the path. So a point is said to be enclosed when the path, if it is enclosed by a closed path, if the path is traversed in the clockwise direction and the point is lying on the right hand side of that path. Let's take an example. Suppose here we are having a closed path and there are 2 points X and Y. Now let's traverse this path in the clockwise direction. So while traversing the path in the clockwise direction, the point Y, it is lying on the right hand side of this path. So this point Y is enclosed by the path. At the point X, it is not enclosed by this path because it is not lying on the right hand side of this path while traversing in the clockwise direction. Let's take another example. Now here the path, it is traversed in the anti-clockwise direction. So here we are traversing the path in the anti-clockwise direction. So this point Y, it is said to be not enclosed because it is not lying on the right hand side. Okay, we are traversing the path in the clockwise direction. So point Y is not enclosed by the path. Okay.